Today you're going to look at reversing the chain rule. So the chain rule is the technique we used for differentiating a composite function, so a function within a function. We looked at a more formal method where we made a substitution for the inside function, and we followed the formula guide for that. We also looked at a more informal kind of shortcut method where we talked about differentiating the outside function, so getting f prime, and multiplying it by the derivative of the inside function. And what we ended up with was both a product and a composite. So we had a composite function multiplied by another function. And that other function, of course, is the derivative of the inside function. So we can reverse this rule so that we can integrate a wider range of functions. And just as with differentiating, we're going to look at two methods. One is kind of a shortcut method, which we call integrating by inspection, as in we're just looking and seeing and recognizing, and then we'll look at a more formal method that can be used without having to spot the answer. But it comes to this idea of recognizing that you have a composite function multiplied by the derivative of the inside function. And when we find the integral of that, we know it started out as a composite function. So one way we can do that is just to spot that. So looking at this here, I've got a composite function. I've got a function raised to the power of 4, and it's also multiplied by another function at the start of this. And if we look more closely, here's my inside function, x squared plus 5. If I find the derivative of this, it would be 2x. And that is what we have located at the front. So we're in this this form that we want to have. Composite multiplied by the derivative of the inside. So it tells us that this must have started out, before it was differentiated, as a composite relating to this. So what we can do is we can think about taking the main part of this function. So we can see the outside of the function is to the power of 4. To integrate that, we increase the power by 1. We divide by the new power. That's just our power rule. And then we'd obviously have a plus c. We can compare this to what we're looking for. If I were to differentiate this is always the way of checking to see if you've integrated something. Differentiate, see if you're back where you started. If I differentiated this using the chain rule, I'd multiply by the power, so that would give me a 5. So let's differentiate this in another colour over here. I'm going to differentiate all of this. So I would multiply by the power, I'd reduce the power by 1, and because it's a composite and I'm using the chain rule, I'd multiply by the derivative of the inside. The derivative of the inside is 2x, and of course the plus c is just a constant, so when we differentiate that, it becomes 0. And now I can see the 5's will cancel, I can move the 2x to the front, and there we are, we've got what we started off with back here. Now, this obviously takes a lot of confidence and a lot of practice to notice these and to figure out how to get back to that original function. So we'll look at an alternative method. This method is called integration by substitution. I would liken it to the way we can differentiate using the chain rule more formally. It will always work if this is the appropriate technique. So let's look at the same function, and we'll look at this integration by substitution technique. Just as before, we choose a substitution for the inside function. So after all that work on differentiation, we should be pretty good at finding inside function. And obviously, if I substitute this in now, instead of x squared plus 5, I could write u. Now, I have a problem in that I am integrating this function with respect to x, but now I actually have u's here. So what I want to do is to integrate with respect to u, so that it matches my variable. But I can use this to help me out with that. So I can differentiate this quite easily. And here I've got a du. So I'd like du at the end of this function rather than dx. And what we can do is we can say that du is 2x dx. And in fact, we can go a bit further and we can say dx is du divided by 2x. Remember to pause if you need to, or rewind if you need to, a bit longer to kind of get caught up with that. So now what I'm going to do is I'm going to substitute in the dx. So 2x u to the power of 4, and then instead of dx I'm going to write this. So this does two things. Number one, it means that my variables match. And number two, absolutely vital, it gets rid of the other x that was hanging around here. We don't want to integrate with two different variables. That's more complicated than is in the scope of our course. So when we do this, changing dx into du, we want it to lead into us being able to cancel out the x's. If the two hadn't cancelled out perfectly, that doesn't matter. We deal with coefficients all the time, but the x has to go. In this case, rather nicely as it's our first example, the 2 goes as well. So this becomes much simpler now. Okay, I can differentiate with respect to u, so I'll increase the power by 1, I'm going to divide by the new power and I'll have a plus c, and then finally I'm going to replace u for x squared plus 5. I might even write that divide by 5 as a fifth because I think it looks a little bit neater. So x squared plus 5 is now to the power of 5 plus c. So two different techniques. One is a bit more intuitive, takes a lot more confidence, is obviously quicker, and a second one that is, it's kind of a fail-safe. This should always work. A couple of notes. So first of all, I mentioned earlier that you must choose, when you replace dx by du, you must lead to the x variables, the remaining x variables cancelling. If that doesn't happen, it generally means you've chosen the wrong function for u. So just take care over that. Doesn't matter if we're left with a 2 or some other number, the x has to go. And of course, if you were not completely sure with your answer, you could check by differentiating it. Okay, so key points then. We're using the variable u for the substitution, and we have to remember to match the du with the u. Let's take a look at an example. We'll try this with both methods. Let's just give us a bit more space. Okay, evaluate the indefinite integral. So that means find the integral of it. Let's start off with that slightly slower method, but kind of our integration by substitution method. So I've got a composite function. Maybe it's a bit easier to see if we rewrite it with brackets. So we've got power of a half. Oh dear, this pen is not going so well, sorry. Okay, so we've got a power of a half. So I've got a composite function and it's multiplied by something else, and I can see that the derivative of the inside, while it's not x, it would be negative 2x, it's the right power of x that there's going to be some cancelling out happening. So that already makes me feel confident that this is all going to work out. There we go, I've got my u, and I'm going to try and find out how I'm going to replace dx. So if I differentiate this, I get negative 2x, and with a little bit of rearranging, I will get du divided by negative 2x. So now let's substitute that all in. So this is what I had originally. Now I'm going to substitute in the u. So that's u to the power of a half. I'm going to change dx for this, du divided by negative 2x. Okay, great, my x's have cancelled. I've still got this dividing by negative 2, but that's okay. If you want, you can rewrite it if that makes it a bit easier for you at this stage. Yeah, just moving that to the front. And of course we can integrate this now. I'm going to increase the power by 1, so I'll get 3 over 2, and I'm going to divide by my new power. Divide negative a half by 3 over 2. That makes negative 1/3. And of course we have plus c. And the final step is substitute back in. Undo that u substitution. Oops, 3 over 2 plus c. Okay, finally we'll look at the alternative method. So the alternative method is to, so I'm just going to start off with the same way, considering our functions. This is the inside function. The derivative of the inside is negative 2x. Okay, I'm just going to write that here. Derivative is negative 2x. So what would be really nice is if this said negative 2x for me, because then it would be really clear that I have the derivative of the inside function right there. But I can't just make that negative 2x, because then this would not be equal to this. This would be a false statement, say that they're equal. So what I did, I've multiplied by negative 2. So what I could do is I could divide by negative 2 as well. Okay, if I simplified that, it would go back to this. But what it means is I've got the derivative of the inside out the front here already. Okay, so I know that I can keep this negative a half, and I can go through integrating. So increase the power by 1. Multiply by the new, divide by the new power. Dividing by 3 over 2 is the same as multiplying by 2/3. Okay, and I'm going to do negative a half times 2/3, which is negative a third. All right, I will put answers for example 2 up, and you can have a go at some of the homework questions.